This is section 10.2a, Parabolas. Let's review again the basic conics. We went over this briefly in the last section, but it's good to look at it again. So these shapes that we're studying in chapter 10 are called conic sections or conics, and they result when you cut a double cone with a plane. Alright, so a circle then is when you cut a double cone with a plane on either one of the cones, such that the plane is parallel to the base of the double cone. Alright, so here we see on the left a plane that is parallel to the base of the double cone, and it's cutting through the top cone, making a circle. An ellipse is when the plane that cuts through one of the cones is at an angle. A parabola is when the plane that cuts through one of the cones does not exit the cone, it only enters it. Okay, so if we look at this plane represented in pink here, let's say that it entered the cone on the left. Well, the angle of entry is such that it never exits the cone, And this cone, of course, you can imagine, extends indefinitely upwards, and the bottom cone indefinitely downwards. Finally, the hyperbola is the resulting conic of cutting both cones of the double cone with a plane that is perpendicular to the base of the double cone. Today we're going to talk about the parabola, and of course we've seen parabolas before. Parabolas are the curve or the graph of a quadratic function. And so in this section, in this chapter, we're going to be studying shapes that may be familiar to you, but we're going to be studying them more graphically. Okay, so the elements of the parabola. You should definitely write this down and even copy the graph down because it's good reference. Parabolas have a focus, they have a vertex, they have a directrix, which is represented with a dotted line because a directrix is not part of the graph of a parabola. It's just a line that is used for reference. And the reason there's a directrix is because the definition of a parabola is a curve determined by the set of all points equidistant from a directrix and a focus. So let me go through that step by step. Okay, notice that I have P here, which labels the distance from the focus to the vertex. And that, by convention, is the variable P. All right, P depends on each parabola. It changes depending on the particular quadratic equation that you're graphing. But for now, we're only looking at qualitative elements, all right, not quantitative. And so just know that P represents the distance from focus to vertex. D, on the other hand, represents the distance from vertex to directrix. Now these other dotted lines here are how we can visualize this definition. Reading through the definition again, a parabola is a curve determined by the set of all points equidistant from a directrix and a focus. All right, so if we look, let's trace this parabola. Okay, so see where the mouse arrow is tracing along the parabola. You can follow that, right? I'm tracing along the parabola, and this parabola is a set of points. All right, and so it's the set of all the points that are on this curve, or if you want to think about it another way, all the points graphed on this set of coordinates would make the curve. Okay, either way you look at it, you can agree that there are many points along this curve, many points. Well, for each of the points, and I have two random ones here. Okay, I'm circling one random one now, and I'm circling the other random one now. So I have two different random points here. Notice they don't have coordinates because we're still just talking about parabolas in a qualitative way, so you understand the concepts. Parabolas are such that the distance from the focus to any point on the parabola is exactly equal to the distance from that point on the parabola to the directrix. Okay, now when we're talking about the distance from a point to a line, you remember from last section, we're talking, of course, about the shortest distance, and that would be the line that's perpendicular to the line in question. And so each of these, this D2 and this D1, are perpendicular to the directrix. Okay, but that is the definition of a parabola. It is a curve determined by the set of all points equidistant from a directrix and a focus. Now we're going to learn a little bit later how the focus works, especially physically, because this is something we see in lenses, we see it in headlights, we see it in a lot of things in nature, things that have a parabolic shape. And so we're going to learn what a focus does and what it's for. But for now, just learn it as part of this definition. If the parabola faces up or to the right, then P is positive. All right, so obviously the distance from between 2 points, the distance between 2 points, we always think of that in positive terms anyway, because, you know, that's how our minds think, that distances are positive. But by definition, with these parabolas, if the parabola faces downward to the left, then P is negative. Okay, so we can see I have 4 different parabolas here. In the upper left, I have an upward facing parabola. In the upper right here, I have a right facing parabola. In the lower left, I have a downward facing parabola, and in the lower right, I have a left facing parabola. And all you have to do when you're doing some of these equations that we're going to do is that you just need to remember that a positive P corresponds to a parabola that faces up or right, a negative P to a parabola that faces down or to the left. Now, of course, I didn't put signs here because whether P is positive or negative, it's still just representative by P because we're still in our qualitative stage. But in this case, you know, if I'm looking at the upper left, P could be something like 2 or 4. But if I'm looking at the lower left here, this parabola that faces downward, P would be something like -2 or -4. All right, so that's just to keep in mind what the sign of P does to the shape. Let's look at parabolas as functions or curves. Now, this is just a little review of what you learned in Algebra 2. There are different ways to express a parabola, and these you've learned already. The polynomial form of a quadratic function is y equals ax squared plus bx plus c. You probably remember this form from when we were doing systems of linear equations, because sometimes problems would ask you to fit 3 points onto a curve that was written in this way. So that's the polynomial form. The standard form of a quadratic function is y equals a quantity x minus h squared plus k. And you may or may not remember this from last year. We're going to see it again a little more later in the year. But this is called the standard form of a quadratic function. And just going through the elements briefly, h and k represent the vertex of the parabola. H and k are, h is the x coordinate of the vertex and k is the y coordinate of the vertex. And a simply indicates whether the parabola faces up or down. Positive is an upward parabola and negative is a downward parabola. And then the size of a determines the stretch of the parabola, how skinny or fat it is. Okay, but you don't need to know that for now. The reason I'm putting these up is because I want you to realize that for any given curve, there could be several ways to express it mathematically. You remember this with lines. You remember there was slope-intercept form, which is y equals mx plus b, and there was also the other form of ax plus by equals c. They're still lines. It's still the same exact line, but they can be expressed in different ways. That brings us to what we're doing today. The standard form of a parabola is, and we're talking about the parabola as a shape. All right, the standard form of a parabola is, if vertical, x minus h squared equals 4p y minus k. If horizontal, y minus k squared equals 4p x minus h. All right, now the h and k here simply represent the vertex of the parabola. H is the x-coordinate of the vertex, k is the y-coordinate of the vertex. And in the horizontal parabolas, it's the same. H is the x-coordinate of the vertex, k is the y-coordinate of the vertex. Now, to distinguish these, just keep in mind that if it's vertical, the x-coordinate will be squared, and if it's horizontal, the y-coordinate will be squared. Now, as far as proving these, the proof is really just based on the distance formula and the Pythagorean theorem. Now, you recall when we were reviewing the distance formula in the last section, and I showed how it's just derived from the Pythagorean theorem. Well, the Pythagorean theorem and the distance formula together are used to derive these two formulas. If you're interested in that proof, it's on page 807 of our books, page 807. It doesn't involve trig, really. It just involves the distance formula and the Pythagorean theorem. If you're interested, you can look in that. It's not going to be too important, but I know that some of you like proof, so you can just look at page 807, and following that proof is probably going to help you understand the concepts better anyway. Let's look at this example. Find the standard form of the parabola whose vertex is at the point 1, 1 and whose focus is the point 3, 1. All right, so basically what you have to do is figure out which standard form you're going to use, vertical or horizontal, and then you just fill in the givens. Now, since this is our first example, I'm going to just walk you through it, and then I'll let you do some on your own a little later. But the reason I want to walk you through this first is because a great first step with these problems is always to sketch. Okay, it helps to sketch. Your sketches don't have to be perfect. They don't have to be perfect, but what they help you to do is they help you to orient yourself, to figure out whether you have a vertical parabola, whether it's facing up or down. They help you to see whether the parabola might be facing right or left. So the best thing to do is sketch a graph. Now we're given some points here, 1, 1, and 3, 1, so I can just put 1, 1, and 3, 1. Notice this sketch is so rough that I'm not even bothering to label the axes, okay, because that's a waste of time. We're just making rough estimates of where 1, 1 and 3, 1 would be, and they would be about here. Because this is a rough sketch, this is not a graph. It doesn't have to be perfect or even close to perfect. Just rough because it helps us to figure this problem out. Continuing the rough sketch then, I can draw my simple little parabola, which again doesn't have to be perfect. And I label my P, which is the distance from vertex to focus. Distance from vertex to focus is P. So since this parabola faces right, I know that P is positive, and I also know that I'm going to be using the horizontal standard form because this is a horizontal parabola. And now you can probably figure out where to go from here. But again, first example, so I'll walk you through it. We know that P equals 2 because 3 minus 1 is 2. This is a horizontal parabola, so the P is going to be horizontal. And so the distance of P is just the x-coordinate that's to the right minus the x-coordinate that's to the left. 3 minus 1 is 2. I now have everything I need to solve this problem. I know that I'm going to be using the horizontal standard form, y minus k squared equals 4px minus h. I know that because of my rough sketch, which showed that the parabola was horizontal, and furthermore showed that p was positive because it faces right. And so now I can comfortably fill in my givens. Y minus 1 squared equals 4 times 2x minus 1. All right, so this 1 comes from the fact that the y-coordinate of the vertex is 1. And this 1 that I'm circling right now comes from the fact that the x-coordinate of the vertex is 1. because h and k represent the coordinates of the vertex. I can put in 2 for p because I figured out that p equals 2. And therefore, the final answer is y minus 1 squared equals 8 times x minus 1. This is the standard form of this specific parabola. The standard form of this specific parabola. Now, those of you who like math would probably figure out, or be able to do on your own, an expansion of this, like multiplying it all out, and then realizing that this exact same curve, y minus 1 squared equals 8x minus 1, can be expressed in the two other ways that I introduced at the top of the screen, the polynomial form and the standard form of the quadratic. It's just all in how you manipulate the terms. So mathematically, we can express the same curve 3 different ways for parabolas. Let's look at another example, finding elements of the parabola. The polynomial form of a quadratic function is y equals negative 1/2 x squared minus x plus 1/2. Find its vertex and focus. All right, so the strategy, and then I'll let you do some of this on your own. The strategy is first you convert to the standard form of a parabola. Now we know it must be vertical. The way we know it's vertical without even sketching is that the x coordinate is squared. Okay, and that's the good rule of thumb. The good rule of thumb for remembering and sorting out the vertical standard form from the horizontal standard form is that if the x coordinate is squared, we're talking about vertical standard form, and if the y coordinate is squared, we are talking about horizontal standard form. One nice way to remember that, if you like, is that vertical lines are always x equals something, right? X equals 1 is a vertical line. X equals negative 3 is a vertical line. And since x equals something are always vertical lines, well, that would correspond to a vertical parabola whose axis of symmetry is vertical. All right, find whatever trick you need to remember that if the x-coordinate is squared, it's a vertical parabola, and if the y-coordinate is squared, it's a horizontal parabola. Okay, now at this point, you should be able to do the rest of this on your own. So pause the video, do it on your own, and then resume when you have an answer. Okay, you probably got stuck, and the reason you got stuck is because this involves completing the square. Completing the square is one of those things that you learned in Algebra 2, but which often is a plague for students, kind of like domain and range. It's one of those things that you learn and then you easily forget because it's just hard to do. So let's go through completing the square. All right, we can just, swap the sides of this equation. That's easy. That's a good first step. And the only reason we're doing that first step is because in the polynomial form, y is on the left and x is on the right, so let's do that here. Now the question is how to fill in the blanks, right? How to fill in what we don't know. This is where completing the square comes in. Okay, so we write our polynomial form, y equals negative 1/2 x squared minus x plus 1/2. And then we manipulate terms a little bit. We're going to just multiply both sides by negative 2 because we want to get rid of that 1/2. So we multiply both sides by negative 2. And I can already see I'm getting slightly closer to the desired standard form. But let's continue. Now I'll bring the 1 over to the left, and so it's 1 minus 2y equals x squared plus 2x, getting even closer. And now I need to get this in a form that I have x in parentheses, right? A binomial, x and a constant in parentheses. And that binomial has to be squared. So how do we do that? Well, we need to do our little trick of completing the square. I add 1 to both sides. Okay, remember you can always add anything to both sides because whatever you do on one side of the equation, you have to do to the other side of the equation. So all we did here is we added 1 to each side of the equation. And what that allows us to do is to write the right-hand side of the equation as a binomial squared. And so that would just be x plus 1 squared. On the left, I just distributed, or rather factored out the negative 2, and so I have negative 2 times y minus 1. And then on the right, I simply wrote x squared plus 2x plus 1 as x plus 1 squared. It's the same thing, just written in a different form. Okay, so now that I have the standard form of a parabola, which is negative 2 times y minus 1 equals x plus 1 squared. This is the standard form for a vertical parabola. The next thing I want to do is solve for p and sketch a rough graph. So we're going to do that on the next screen. I rewrite my standard form that I found. Now I want to solve for p. And all I have to do is just fill it in, right? Because if 4p is negative 2, then I just write it 4p equals negative 2 and solve for p. And all I did there is I just equated this negative 2 with 4p because that's what appears in the standard form. 4p equals negative 2, so p equals negative 1/2. Okay, now is the time to do the rough sketch, again, only to help us orient ourselves. So we do our rough sketch. We know that the vertex is at negative 1, 1, because that's what I get straight from the standard form, hk. Okay, so if h is the x-coordinate of the vertex, then it must be negative 1 because this in the parentheses that I'm circling right now, this in the parentheses is x plus 1, which is the same as x minus negative 1, x minus h. And so h is negative 1. That's why I have negative 1 written here. And this is y minus k that I'm circling now with a mouse arrow. And k is the y-coordinate of the vertex, so y minus k. This is 1, and therefore my vertex is negative 1, 1. That I got just directly from the standard form. Now, where I am going to use the information that p is negative 1/2 is the following way. First of all, it's negative, so it must go down. And therefore, I write it this way. Negative 1, 1/2. These are the coordinates of the focus. And I use the fact that p is negative 1/2, and so follow my mouse arrow now. This distance that I'm tracing right now is p. And that p is negative 1/2, which means it goes downward. And therefore, 1 minus 1/2 is 1/2, and that's why the y-coordinate of the focus is 1/2. So now with this rough sketch, again, it doesn't have to be anywhere close to perfect. It just helps us to orient ourselves. I can clearly see that the vertex is negative 1, 1, and the focus is negative 1, 1/2. And that is what we set out to find in the first place. The classwork is page 740. Write these numbers down, and you will need to complete the square in some of these, but we'll do them in class. So if some of you are struggling with completing the square, we can help each other out in class.